DMMAS is the last tool we will see in this training. DMMAS is a simulator, but what does it simulate? It simulates a network, a machine, but it does so in a coarse-grained manner. And this is because DMMAS has to be fast and give trends on how the application will behave. It doesn't have the focus on being precise, but fast. To do so, DMMAS uses a very simple model. The model is depicted in here, the top right, the image. The model uses nodes with their CPUs, with their local communications by memory, and nodes communicate through a network that is characterized by bandwidth and buses. And the connection to each node to the bus is characterized by bandwidth, by the number of links and latency, sorry. All these parameters can be defined by the user and allow them to perform two types of studies: parametric sweeps and what-if analysis. Parametric sweeps, we want to do those when we have more than one version of the code, and we want to measure the impact of the bandwidth as shown in this image here at the bottom. We have the bandwidth in the x-axis and efficiency on the y-axis. And reading from right to the left, and then we have bandwidth reducing from 124 to 1 megabyte. And we see the different versions of the code behaving different and having different impacts on their efficiencies. The ones that staying close to 1 are the ones that are less sensitive to the bandwidth. This would be an example of a parametric sweep. The other type of analysis, the what-if analysis, allows us to ask questions, allows us to look into the future, for example. What if I had a faster network? What if I had a faster CPU? What if I had asynchronous communication? Okay, this is nice. I can ask what will happen to my application with a different machine, with a different network, with different type of communications. DMMAS allows us to do that. And finally, Paraver and DMMAS can work together. We can launch DMMAS from a Paraver window, from a Paraver timeline window, and apply the study only to that part of the execution of the application. The output of DMMAS are Paraver traces, so we can do the same kind of a study we have seen until just 5 minutes before with the simulated traces. And this allows to compare the simulated traces easily with the original executions. Let's do an experiment. Is our application sensitive to bandwidth and to latency, to both? Okay, in the left side, we have the real run of MPI RE, running 32 tasks with a latency of 5 microseconds and the bandwidth of 1 gigabyte per second. In the first half of the execution, we see how the processes in red, the red region, stops all the processes stop at the same moment before starting with a blue color. I forgot to mention that red regions mean being in MPI and blue mean the application is computing. So MPI communications block at the same time, just before starting with computing again. This means that in this part, we're doing a collective communication. And here in the second part, it seems that we're doing some kind of reduction. With each process, communication with the previous one in a tree-like manner. Do you see the yellow lines here that go from the process to the previous process? So this means that we're going to communicate. This is a communication line going from one process to the previous one. So from this original trace, we will do two kinds of simulation. The first simulation, we will increase the latency by a lot. We will go from 5 microseconds to 1000 microseconds, to 1 millisecond. And we will compare the executions. What do we see here? We see that a small yellow states start to appear, but the total execution time more or less remains the same. So it doesn't really seem affected by latency, limited by latency. And what about bandwidth? Let's reduce the bandwidth just by one order of magnitude. Let's go from 1 gigabyte per second to 100 megabytes per second. What happens now? Is this image in the bottom right? So do you see how the reduction here at the right side enlarges by a lot? So here it was about, I don't know, 10% of the iteration. Here it's almost the half of the execution. The application is doing many communication at the same time, and they share the bandwidth. So if we reduce the bandwidth, we are affecting the throughput of the network and increasing the time we are using to communicate. So we could say that this application is limited by the bandwidth. Let's do a second experiment. Let's do a parametrics suite right now. We will be using WRF, run at 3 scales from 128 to 512 processes, using a bandwidth of 256 megabytes per second and the latency of 8 microseconds. We will evaluate the latency, the bandwidth, and contention. For latency is the graphic we see right now on the slide. The x-axis is showing the different latency values from 0 to 32, 0 meaning no latency, so 32 microseconds. And the y-axis representing the speed up with respect to the original. 1 being the original is where we have the execution with 8 microseconds. So this point will be the original runs. We see ups and downs, yeah, but in the range of, I don't know, 994 to 1002. So very, very small changes. So we can conclude WRF in neither of its versions and the scales is sensitive to latency, so very small deviations. And what about bandwidth? So we fix the latency at 8 microseconds and modify the bandwidth. Here in the x-axis now we have bandwidth, and in the y-axis we have efficiency. So now we see different behaviors. If we stay at 1, it means we are not affected by bandwidth. And reading from right to left, the ARW version of the code, represented by the pink, orange, and purple lines. Yesterday I saw it as a purple. Today I see it. I don't know what the reddish. These three lines here. drop very soon as the bandwidth is reduced. So we see a strong drop in these three lines with the bandwidth. But NMM stays around 1 until 64 megabytes per second, where it drops to 20% efficiency. So it is clear that the ARW version is more sensitive to bandwidth than the NMM version. And what about contention? In the last image, we are reducing the number of buses. In the x-axis, we have the number of buses, and in the y-axis, we have the speed with respect to the original trace with the original execution with full connectivity. Again, we will read from right to left. We see that all ARW scales are sensitive to contention. ARW lines drop as we reduce the number of buses. But in this case, the MMM, only the highest process execution is only the NMM with the blue color with 512 processes reduces increases the contention with the scale, but just this and the speed with respect to the original execution drops. Let's continue with a real case. Some years ago, developers of I have a question in the chat. So contention is when I cannot connect because the bus is I'm limited by the bus. So I want to connect, but I don't have a space to send my message. So in the original trace, we assume there's unlimited number of buses, so I will have no contention. And what we do here is start at a large number of 36 and reduce the number of buses. Okay, in this real case, the developers of Spectrum 3D asked us if it was worth moving their application from synchronous to asynchronous communication. This can be quickly answered by simulating an ideal machine. So if I have an ideal machine is when I have unlimited bandwidth and no latency. The effects of communications will have to disappear, right? But in here, we see that they don't disappear. In fact, the execution is not modified by a bit, so it's exactly the same as the real run. Same time, same structure, same everything. So it doesn't seem that this application will benefit from asynchronous communications. But we can do some other tests. So we can see how this application is affected by the bandwidth. And what we did was to start reducing the bandwidth from the predicted run on Mare Nostrum, which is the same as the real run. And we start by reducing the bandwidth to 100 megabytes, no change. 10 megabytes, we start seeing something, but not really. 5 megabytes, but until we reach 1 megabyte per second is when we see some change in the application. So this is not affected at all by the bandwidth. So we can use a very simple network, a very old network, and the application will behave very similar to what it is behaving. So I mentioned the ideal machine. I mentioned that it is an impossible machine with infinite bandwidth and zero latency. And it is used to describe the intrinsic behavior of the application. But why do I care simulating this machine if I will never have this machine? First of all, it says that if I don't improve in an ideal machine, there's something wrong in my application. So if the best machine, if the best network in the world doesn't improve my machine, I have some structural problem in my application. This is an example of gadget with 256 processes. In the real run, here at the top, we see the different MPIs, or gather, or reduces, out walls, and receive. These calls should go away in the ideal machine. So immediate communication, right? So this code should disappear. If they don't, the problem is not in the transfer of data, but on serialization or load balancing. One process is waiting for another process to finish. So in this case, they disappear a bit, but we still have some of these colored lines here. So this is not caused by the network, but by serializations. Okay, now, instead of talking about the future, the ideal machine, let's talk about today. Let's use accelerators. Sorry. Let's talk about, first, let's talk about the future. So what will happen with a new machine with different network parameters and different CPU ratios. So let's think about, I don't know, 4 years time. We're using the same gadget application, and we're looking at the scalability with 64, 128, and 226 processes. If I had access to a machine up to 64 times faster, so the z-axis is the CPU ratio, the x-axis is the bandwidth, and the y-axis is the speed up. Okay, the maximum obtained speed up for the 64 processes execution with 64 times faster CPU and the fastest network I'm simulating is around 120 and 130. Sorry. So this would mean that ideally, if I increase the scale, this speed up should remain the same, but it's not the case. In the 128 case, I get around 105 speed up. And in the case of 256, I get around 100. So this happens because of the serializations we saw in the previous simulation. If we have more processes, the serializations will affect more processes, which translate in more processes waiting for more processes. So serialization go up with the scale. But what about now? What if we are not looking to the future, but to today? And well, why don't I have this slide? Oh, yeah, is this. And instead of accelerating all the computations, I choose to accelerate just the most important clusters by using, for example, accelerated CUDA devices. Okay. In the previous example, we were accelerating everything. Now we only will accelerate the important the important clusters, the important regions. And in here, we start by accelerating around 93% of the code, 97 and 99. And we see that we only reach, even if we accelerate up to 99% of the code, we only reach around 18% of a speed up from the 100 times faster that we had in the previous slide, right? So this 1% of the code is killing the speed up. If we don't accelerate this 1%, we cannot obtain all the benefits possible, all the possible benefits, right? Now, what else can be done with DMMAS? We can compare different code versions, the different paradigms of communications. For example, synchronous and asynchronous communication. We have synchronous in the left and asynchronous in the right. So what do we see here? Which one is better? In the ideal simulation with synchronous communication, we already see problems of dependencies. Do you see this ladder pattern here? So that processes go in diagonal here, the computations. We don't see this in the asynchronous communication one. And what happens if we start degrading the bandwidth? We degrade, and in the synchronous communication example, this ladder pattern gets worse and worse and worsen as we reduce the bandwidth, right? On the other hand, in the case of asynchronous communications, this does not happen, and we can go down to 100 megabytes per second from the ideal execution, and we don't really see a change in the behavior of the application. So we can conclude that the synchronous version of the code is much less sensitive to network. Finally, so we have to go down up to 10 megabytes per second to see some issue in the asynchronous communication version. Finally, DMMAS can also help us to choose what should I improve first. By combining the tools we saw this morning in the previous session, by combining clustering with DMMAS, we can select a region, one of the clusters, and accelerate it or balance it and see the benefit we will obtain if accelerating or balancing this part of the code. In this example of Pepsi, we have two unbalanced clusters. These are clusters, green and yellow. So you see the zigzag here. The yellow one also has this here. I don't know if you can see it, but also we can see this here with this unbalanced both in instructions and in IPC. And what will happen if I accelerate the first cluster, the green cluster, to have the same IPC of the second cluster? How much benefit will I obtain? DMMAS can answer this by accelerating to the same IPC of cluster 2. And if I do this, I obtain a 13% gain. So if I somehow buy some accelerator and move this first cluster to this accelerator, I can obtain a 30% of improvement. Okay, that's nice. I spent, I don't know, some money, and I get a 30% benefit gain. Great. But what if I think a bit about the algorithm and balance both clusters so this zigzag disappears? So what happens if I go from this to this? What would be the benefit? So with DMMAS, I can do that. And with this, I obtain a 19% of improvement. So in this case, without spending any money on new hardware, I can obtain more benefit than if I buy some accelerator. So maybe it's better to think about a bit about the algorithm and not spend any money. It's important to note that DBMS is not telling you the difficulty of doing one or the other. Well, the difficult, so it just says the benefit of doing one or the other. So then you have to evaluate what's your first interest. Okay, this is what DMMS can do. Let's do a quick demo to show you how to do things with DMMS. I will start by simulating. Okay, let me open Paraver. Okay, the first thing we usually do with, I already have the traces generated. You will generate the traces in the hands-on after this session. The first thing we usually do, let me open first the original file, the original trace. The first thing we usually do is to simulate the actual machine. So we do a nominal execution. We do this so we know that the simulator is correct, that we have the correct data, and we can move to the other simulations.
Well, more than that, you have the correct data. Basically, you need a run as a reference. So if I try to model the execution, then I really have an estimator for the parameters of of latency and bandwidth and length and so on. So once I verify I have something similar, then I can work on an improvement or a reduction because I know I'm close enough to this initial situation.
Thank you, Judith. So I'm characterizing my machine, the execution on my machine. So that's why I have the nominal execution. So let's take a look at my nominal execution. So let's take a look at the structure of the application and at the efficiencies I get. This is the original run. So I have this structure with this is Lulesh. We are always using Lulesh in this training. So we know that we have this unbalanced region, and we have, this is a shop, we have some iterations of these, of the algorithm. And these are the efficiencies, 89% parallel efficiency, 99% communication, so almost perfect communication. And this is the load balance, 90%. So we have some imbalances here that we see here. So we modeled our machine. Let's open the structure. This is a simulated trace. So you see that it has the same structure. I can copy and paste the time. So we have the same time scale. And if I open the efficiencies, so to be sure I have the same efficiency in the simulated trace, 89%, 99, 90%. So I have characterized my machine. From here, I can do the experiments, changing the parameters in this nominal execution and go into a faster CPU, faster network, or all the things we did when I explained in the slides just some minutes ago. So, for example, another simulation we usually do is the ideal simulation. So let me open the trace. I think I didn't open. Let me open the trace for the ideal machine. And let's check the same parameters here. So let's check the useful duration. Let me copy and paste the time. And let me open the efficiencies. So again, this is the ideal simulation. So remember, ideal means instant infinite bandwidth and no latency at all. So I have the same numbers here, 89, 99, and 90. So with the impossible bandwidth, with the impossible network, I don't get any benefit in Lulesh. That's because I'm limited by this unbalanced region here, that even if I go very, very fast, I don't obtain any benefit. So what to do? From the slides I explained before, I could try with a slower network if it's sensitive to bandwidth or latency, if I could try to accelerate the computation, but I think the best thing to do is to understand what will happen if I balance this region. So this is the problem with the application, right? So what will happen? For this, I have to open the cluster view of the trace and compute the average time, for example, that the unbalanced cluster, which is the unbalanced, no, so the unbalanced cluster is this yellow cluster, and compute the average time of this yellow cluster. To do so, I have to change the statistic here. First of all, let me unzoom this and go directly to the summary. Let me go to the cluster 2. This is percentage of time. I want to change the statistic here in the main parameter window. I want to select average burst time, so the average of each computation. And here I get 83,000 microseconds. So I can put this value to DMMAS for this cluster and obtain a new trace with the balanced computations. In this case, I already generated this. It's this trace here. I will open the useful computations. Useful computations are here. So let me copy and paste the time. Oh, I got some benefit. I got a 10% benefit here. And do you see that the region, the yellow region here, the time I put on DMMAS was 80,000 microseconds, not 83,000, but okay. Then we see 80,000 here. This number here at the bottom is the duration of this region here. So if I balance this cluster, just by balancing this cluster, I get a 10% of improvement. So nice. I don't know if it's easy or not. I can look at it, but at least I know I will improve, right? Great. So let's take a look at the efficiencies. The efficiencies, so now we have perfectly balanced regions, and the efficiencies went up by a lot, from 90%, not 90 in the nominal, sorry. We went up to almost 99. Communication stayed the same. So we are doing the communications as fast as we were before. And load balance improved to almost 100%. So we have perfectly balanced computations now. Great. So what else? Now I think it's your turn. So we have some question about this you can ask now. If not, we can move to the hands-on. So you do some experiments with DMMAS. And okay, your turn. I will do the experiments with you, if I can. So there's no question, something to add. Okay, let's move to the hands-on. Let me move this here and start with the hands-on. So for the hands-on, we will need to connect. I have on the left side, this is my machine, my local machine. On the right side, I will connect to Mare Nostrum. Okay, the first thing to do to use DMMAS is connect to Mare Nostrum because it's not, we have not installed DMMAS in our machine. Okay, we go to tools hands-on/DMMAS. Do you see the terminal, right? Do you want me to increase the size of the font, or it's okay like this?
We see it, and for me, it's fine.
Okay, perfect. So to use the here, you will see if you followed this morning's hands-on, you will see that this in this folder in tools hands-on/DMMAS, there's 3 sim links, the symbolic links, that are pointing to the clustered trace file you generated this morning. This morning with Herman. If these links do not point to anything because you had problem generating the trace, so you can redo these sim links by doing this and use the trace file at dot traces clustered. Well, you can do this, I think. Or even better, just in case this. You can regenerate these soft links like this. Okay, we have these soft links generated. Now we have to load the DMMAS module load DMMAS. And the first thing to do is to convert the Paraver trace to a DMMAS trace. So let's run this command. We can use star.prv as we only have one PRV file here. And let's give a name to the simulated trace. So prv2dim, star.prv, and a name of the simulated trace .dim. We hit enter and the trace is simulated. And now if you do an ls, we see the new file here. Okay, with this file, we will run DMMAS. The first we will do is to simulate the nominal.
Lau, there is a comment in the chat saying that the module load DMMAS in capitals. Well, it put DMMAS. It should be DMMAS.
Yeah, it's DMMAS with an M.
Okay.
Maybe it's trying to find the module and it's not finding the module, and that's why. Okay, thank you. Okay, we'll first do our first simulation with the nominal, which will be the nominal simulation. For this, we will use this file, the mn.crg, which is a configuration file for the Mare Nostrum machine. There's a lot of text. at the start, there's a description of each section of the configuration file. If you want, you can read through it. But the interesting part, the actual configuration is at the bottom. So PRV, so we're missing a 2. It's PRV2, the number 2, dim. So this is the configuration of the machine, the number of nodes, the connection between the nodes, how many tasks per node we want, and other things. So in this case, we are using a machine with this latency and this bandwidth. Okay. So let's use this to simulate Mare Nostrum. So to simulate our application in Mare Nostrum. So for this, we will run this command, dimemass with capital D, dash capital S 32K, dash dash dim to select the dimemass, the generated dimemass trace file, and dash P nominal.prv, which is the output file, and finally the configuration file, mn.cfg. Maybe I can. Okay, better. So this is the configuration file. We hit enter. It starts simulating. It's fast. It simulated our machine, our application with our nominal machine, our Mare Nostrum. So let's take a look at this file. Let's first let's go to your folder wherever you want in your laptop, in your machine, and copy this generated trace file to our machine. So we issue this command, scp training tools hands-on dimemass nominal, to copy this. Okay, it seems I'm going too fast, right? How to generate the trace file? Yes, it's the prv2dim command. Or you mean this or the simulated trace file? To simulate, you have to issue this command. Dimemass -s 32K, select the dimemass trace file, select the output name, and select the configuration file you want to use. So we have copied with the scp command the nominal trace to our machine, and we will open it to Paraver. We open it with Paraver, so let's open Paraver. Let's open not only the nominal but also the original file. So let's open the original and the nominal. No, it's not this. And the nominal. Right. And let's check that we have the same structure and efficiencies. Okay, these are the structure and the efficiencies of the trace file we generated yesterday. And let's check the nominal simulation. Let's check
an error in the chat, and I think the reason is that the trace file does not exist. So that should be the link.
No, maybe Error accessing, maybe it didn't generate the dim file.
For the clustered or without the clustered?
For the clustered, we are using the clustered file. Maybe you missed the prv2dim command, this command. Before simulating, we need to issue this command.
The reason, let me explain, the reason to translate the trace from parameter to DMMAS format is because parameter traces, what they express is what happened, okay? Are timestamp data that says at that instant of time, this happened, okay? That relative instant of time from the 0 at the beginning of my execution, this happened, okay? So there are things that happens a long time. While what DMMAS trace file require is the use of the resources. Is I am sending a message of this time, of this size to this guy. I am computing for that long, okay? So that's the required translation basically is to translate those timestamps to resources requirements. Okay, so you always do you use DMMAS, you have to do these two steps. First, and this is only done once per trace file, translate from paraver to DMMAS. And then once you have the DMMAS trace file that is .dim, you can do the simulations.
We'll leave these two commands here. The right side, you have the commands needed to generate the simulated trace. Thank you, Judith. Okay, where was I? Okay, yeah, I was comparing the original execution with the nominal execution, with the nominal simulation. So the structure, if I copy and paste the time, let's do this so we have the same scale in the timeline. So we see that they actually last the same amount of time. The structure is the same. So let's check the efficiencies if they are the same. Let's open the efficiency also for the nominal execution. So 89, 99, 90. So we can conclude that we did a good job simulating our machine. So from here, we can start doing other simulations. Please, I don't know, select the green mark if you reach this point. If not, I can re-explain some of the steps or ask in the chat. Okay. It seems that people are following. So let's do our second simulation. Our second simulation will be to simulate the ideal machine, right? To see if this improves with a faster with an impossible network. For this, what we do is copy this to ideal, the nominal configuration file to the ideal configuration file. You already have this in the folder. This file should exist. So let's open it. Ideal.cfg. Let me move this here. So the configuration file is the same, more or less the same. We have the same sections here. Let me try, I think. No, okay, nothing. And what if I do this? Can I do? No, okay. Doesn't matter. So what do we need to change here? We need to change this bandwidth here. So between nodes, we have infinite bandwidth, and we need to we have infinite bandwidth, and we need to change this and this to 0, to ideal. 0 value. 0 in DMMAS means either 0 for latency or infinite for bandwidth. So we need to change these 4 numbers here to 0.0. We will have this. With these modifications, we have an ideal configuration file, an ideal machine configuration file, and we can run the DMMAS command. Instead of using the mn.cfg file, we will use the ideal configuration file. So we issue the same command, DMMAS, using the same .dim file. Now we are giving an ideal.prv name to our simulation, and we are using the ideal.cfg file. We hit enter, and we obtain the simulated trace file. So here, let's copy this to our machine. So do scp from your account at Mare Nostrum, to hands-on, DMMAS, and ideal.star to your home. Hit enter. Insert the password. Oh, yeah. Do you have it? I will leave the simulation comment here. Okay, we have 5 minutes. I think I will show this simulation, this ideal simulation, and we leave the rest for the afternoon. In the afternoon, you will play yourselves with DMMAS. So let's check this ideal configuration file that we just copied to our machine. Let's open it with Paraver. File, load trace, to DMMAS, open the ideal.prv file, and let's open the same views, the useful duration one, and we will copy and paste the time from the nominal simulation to the ideal simulation. So no change in the structure, no change in the time. So an ideal network does no benefit. So it gives us no benefit. Let's check the efficiency just in case if they got any better, but as we can assume they didn't move at all. So we have the same parallel efficiency. We have
Can you zoom in one iteration just to show? Let's basically the first one, okay?
The first one, yeah.
Yeah, and do the same for the 3 traces.
Right.
Well, synchronize. Let's copy and
right,
synchronize or paste the time. Okay, and basically, if you make it just to eliminate the small gap at the beginning in the top one of the second iteration, so don't take the blue of the second.
Yeah, this, like this.
Yeah. So, well, basically there is a very, very teeny improvement. Okay, like it's less than 1%. Okay, because there is some transfer time, but it's so small. You can see that also if you synchronizing the gap before the imbalance region. Okay, it's a
Here?
very, very tiny difference. Yeah. Okay, this is the to make it faster, but it's also a small amount of time. Okay, so ideally it's really reducing that transfer time. Okay, but it's really so small that you don't see.
We see an increase here in the communication efficiency from 99.30 to 99.9.
To show where you can perceive this very small increase.
Yeah, okay. Thank you, Judith, for this.
I think if you zoom into one of the last iterations, you will see better the difference.
But then you see the accumulated difference.
Yeah.
Okay.
Yeah.
That this is not fair. This is not how much this is how much I improve. Let's say if you do for the last computing phase, the imbalance, you will see the total benefit. Okay. But it's really small. So
in fact, we see here that this last iteration starts a bit earlier here. Yeah. But it's very, very, very small. So, okay. Thank you, Judith. And okay, if you got to this point, I think it's time to go to lunch, right?
Yeah.
In the afternoon, you will play a bit. We will play with the CPU settings, for example, and we'll try to reduce the bandwidth and things like that. And we will also try to accelerate one of the clusters. So you will have a general idea of how to use DMMAS. So there's a question in DMMAS in the chat, sorry. Well, maybe the nominal simulation is not as precise as it has to be. So it's my fault, probably.
Yeah, well, it's not your fault. Basically, when you want to generate the nominal, is the harder scenario to simulate. Because you have, let's say, you cannot put the parameters of the hardware because it's at the level of the MPI software stack. So from the MPI underneath, whatever it is, this is the latency and bandwidth. Okay, so that basically even depends on the MPI flavor.
Yeah, because DMMAS, I didn't say this in the series. Thanks for.
So if you want to adjust it properly, what you have to do is run some benchmarks, many of them, few of them at least, on a new platform to adjust so much these parameters. Okay, so that we do an approximation. So if I get a simulation closer enough, I consider that's acceptable. Okay. But ideally, DMMAS, let's say, DMMAS used to be more optimistic than negative. Okay. In many cases. But it is true. If you want to make a pure adjustment of the nominal, that's much harder.
Okay. Thank you, Judith. So it's important to remember that DMMAS simulates both the machine, the hardware, and the software stack. So it's the thing that Judith said. So we can have a machine that has, I don't know, 100 gigabit per second network, but the application doesn't use it at all, or it is limited by the MPI implementation or whatever. So DMMAS takes into account this, and when you are generating the nominal configuration file, you have to be aware of that, right? Okay, so let's close this session. Let's go for lunch, and we meet again at 3.
No, at 2. I will come back at 3, but you come back
sorry,
at 2.
At 2. It's 1 p.m., not 2 p.m. Sorry. Yeah. And let's meet again at 2, and we will do some more exercises with DMMAS and Paraver, and something else, and the knowledge test.
Just a reminder, the students for the university that want to claim the credit that this training offers have to do the exercise in this afternoon, and then I would like to have a feedback from you. You will be working teams, and I will have a feedback to confirm that you have acquired the knowledge that is presented. Okay, I'm not going to be very strict, but I want to know that you understand a minimum from what we have explained. Okay, so I recommend that everyone keeps on this exercise. I think it's a great way to validate what you have been obtaining from this training, and also to get more confident on your knowledge. Okay, so the idea is that we will start that at 3:30. That give us 2 hours. Okay, I recommend to do teams of 2-3 persons typically, as we are a huge team of people. If people want to be 4 persons, that kind of be the limit. We will create breakout rooms, so you will work on teams. You will be able to talk with your team. So if you have some friends in this training, you can group yourself. Okay, and the students have to be grouped between them or alone, but not mixed with other people. Okay, because the evaluation is different. Then I will do the evaluation for the students. For the other guys, that's up to you. And if we have time, I will show you how I will do this analysis. Okay, so have a nice lunch and see you later. Thank you very much.
Okay.